This is Section 2, Group 5, and our group did Flap AI. And as you can see from our team, it's Kevin Greif, Miles Bimrose, Chase Miller, Kara Ravazio, and Patrick Bouchon, as well as Seamus the 13th.
The goal of our program, Flap AI, is to create a computer program that utilizes machine learning to play Flappy Bird. The program uses the existing online code for Flappy Bird in MatLab's libraries, written by Mingjing Zhang. Instead of teaching the computer the correct strategy for Flappy Bird, we will allow the computer to randomly explore the various states of Flappy Bird, recognize patterns in the rewards it receives, and maximize those rewards to learn the correct strategy. The target is for the machine learning algorithm to surpass average human proficiency in Flappy Bird, arbitrarily defined to be a score of 25 points.
Some assumptions and limitations we faced while making Flap AI include the assumption that average human proficiency is defined to be 25 pipes. In reality, many people score below this threshold. Some limitations include the propensity for the Flap AI program to accept less than ideal strategies because it learns through trial and error with the Q learning algorithm. As a result, it learns a less than perfect method of play. For example, it jumps 1 pixel above the ground, even though this is not optimal. To check the performance of our program, we compared our results to the results of a similar project performed at Queen's College. And their results were about a score of 150, which is comparable to the high score of 162, which our best run program achieves.
So this is the Q learning algorithm that we use to teach our program to play Flappy Bird. What it does is it assigns a reward value to every state that the bird could possibly be in. In our case, these reward values were 15 if the bird was alive and negative 1,000 if the bird was dead. It then feeds this reward value into the equation that you see in the middle, multiplies it by the alpha value, which is essentially the rate at which this algorithm learns, and then stores the reward value in something called the Q matrix. Now, over time, as the program explores more and more of the state space, this Q matrix becomes populated with desirability values, and the algorithm can then make decisions on whether to jump or not jump based on the numbers that are stored in this Q matrix.
So this is our GUI for the project. You can change the alpha learning coefficient with this drop-down menu. Then over here you can change how many trials you're simulating. With this slider, you can also type it into this box. Then when you hit the run button, it animates it over here, what the Q learning matrix learns. So red being that it learns that it dies, green meaning that it learns to jump, and blue meaning that it stays alive. And then once it's done animating, it runs it over here for that learning state. We also optimized a Q matrix to play the game to the best of its ability that we thought was possible under the current circumstances. So when you hit best run, it loads that matrix up, and then it displays it over here. So this one averages around 18 trials. In that case, it didn't do very well, whereas the average performance is about 5 or 6.
As you can see on the slide, we had a graph that showed different alpha values and how quickly and effectively Seamus learned. So with the highlighted line of 1.0, that would be a quicker learning coefficient, and thus Seamus would learn a lot faster. As such, he would reach a plateau much lower than that of the lower learning coefficients because it would put in values in not necessarily the right places. As you can see from this photo, we can use the GUI to change those lines and evaluate different learning coefficients to find which is the best and most effective in finishing the game the best possible way. Thank you for listening to our presentation, and as you can see here, we have some final references that we use to help us with this project. Thank you.